So, welcome everybody. I'm joining you today from Newton's garden. So, this is where motion started, and the story goes anyway that he was under an apple tree, and while he was under that apple tree, he noticed an apple falling, and this is where the laws of motion came from. If we look at our handout, we can see that Newton had some laws he came up with for his Principia Mathematica. And let's go through these laws and see how they apply to this apple. So the first one, every object, I'll put it in English, plain English terms that we use nowadays, an object will remain as it is unless acted upon by another force. So an object will remain still unless it's acted upon by another force to make it move. Or it will continue in a straight line, moving at constant velocity unless acted upon by another force. So what Newton observed here with this apple is that when it fell to the ground, everyone before that would have just assumed that everything falls to the ground. But Newton, with his first law, said that some force must be acting on the apple to make it move. Otherwise it would remain where it was, it'd just stay there floating. So another force must be acting on it to make it move. This force obviously is gravity. So that's his first law. Second law is that force equals mass times acceleration. This is Newton's law of unequal forces. So why did the apple drop at the speed it did? And do all objects fall at the same speed? Well, Newton here was standing on the shoulder of giants, as he called it, because he was working from what Galileo had already discovered by falling objects, that actually they fall at the same rate. Air resistance affects them, but if air resistance wasn't there, they would continue to fall at the same rate. This is quite profound, really, that there was no way of actually showing this back then. This was all done just by theory, but he was accurate, he was right. And of course he was correct because it falls at a constant pace. And we know this because the force acting on it from the first law is gravity, and that is constantly acting down at 9.81 meters per second per second. Doesn't matter how heavy the object is, that's acceleration due to gravity. If it's got a big surface area, then wind resistance is going to have an effect on it, but air resistance withstanding, everything should fall at the same rate. We're fortunate enough on Earth that anything passing by that comes into our atmosphere burns up, but you've only got to look up at the moon on a clear night and see that body has no atmosphere, and anything hitting it hits at remarkable speed because it has no air resistance to slow it down, and it obeys Newton's second law precisely. The force that's acting, the acceleration, is about a sixth of what's on Earth, and even so, without an atmosphere, it completely pounds the surface. And then Newton's third law, this is the one that everyone hopefully remembers a bit more than the others, that every action has an equal and opposite reaction. So if I was on frictionless roller skates and pushed you, and you were on frictionless roller skates, we'd both fly back at the same speed. So if I go and push a car, then there's that reaction against my feet on the floor to push forward. That action has got to have a reaction. And obviously if I was on ice, I wouldn't be able to push that car forward because there'd be no reaction to push against. It'd be too slippy. So hopefully have a look over the next week at Newton's three laws. They're everywhere around, and one of the ways of really understanding the physics here is to keep looking at your surroundings and think, where's Newton's law applying there? When I'm feeling pushed back in a car, when I'm accelerating, Newton's second law taking effect. When you see something on the news about a satellite going up and carrying on at a constant trajectory unless acted upon by. When you're pushing against something and you feel the push of being pushed back, you're reacting against it. Newton's third law. So it'd be really good to come up with some examples of these over the next week. I think it would definitely help. So first of all, up there, we've just looked at what the laws of motion are. We looked at Newton's three laws. We're going to be looking at some more things on motion, and we're going to be trying to solve graphically and algebraically the same problems. This is going to come up in assignments and exams, whether you're at uni, college. This is going to come up at some point, and it will ask you to solve it graphically, to solve it algebraically. There's advantages and disadvantages for both. If you solve it algebraically, it's really accurate, it's really neat, you can do it quickly. The problem is you've got to remember all the algebraic equations, and there's five. There are five algebraic equations. The graphical method is a bit more long-winded, it's a bit more troublesome to draw out, but once you get that idea in your head, then you don't need to remember the rules because it's just working out the areas and gradients of geometry. It's quite straightforward. So there are fors and against. There are advantages and disadvantages to both. So let's have a look. So S is displacement, and the SI unit for displacement is meters. Now, just quickly, the difference between displacement and distance is that if we were to have a point here and a point here, then the displacement is literally the shortest path between the two. However, when you're in a car, when you're going anywhere, it's very rare that you go in an absolute straight line. Often we call it as the crow flies, don't we? But in reality, you probably go all over the place and sometimes even past and back. That's distance that we've travelled. This is displacement. And it's interesting that if we were to go to college or to work, and this is our home here, and this is work, then if we travelled all the way to work and all the way back, our displacement would equal 0. But our distance, which is a scalar quantity, would equal maybe 5 kilometers, because we could have travelled all the way here 2.5 kilometers and then all the way back 2.5 kilometers for a total distance of 5 meters, but our displacement would be 0 because we've not moved from where we started. So that's the difference between displacement and distance. Vector has both magnitude and direction. So the next points on up here are u and v. These are both velocities. Velocity is to speed what displacement is to distance. So velocity is a vector. It has direction and magnitude, where it's going, where speed could be your average speed going. The average speed in London apparently is about 5 miles an hour. But you could get up to like 40 for a bit and then down to 3 for a while and then back up again, where a velocity is a constant and it's in an absolute direction. And then we've got acceleration. This is our rate of change of velocity. So if we think about this, that's the force you feel when you're in a car and you get pushed back when people accelerate hard, or when they brake really hard. That's deceleration or negative acceleration. And when you're on an airplane, you feel yourself being pushed back in the seat when it takes off. But once it's going at 500 miles an hour, you're cruising along, no acceleration, because you're going at a constant velocity. So acceleration and velocity are different, okay? And then time, the SI unit for time is always seconds. So if you're given a question and it's in hours or minutes or days, for some things like in space travel, days of acceleration is what's required. Then you need to convert it to seconds. Okay, and just a quick one on conversion, because we live in the UK and miles are quite common. So if we want to go between 1 mile is equal to 1,609 meters. And also there are 3,600 seconds in 1 hour. So if we wanted to convert something like 60 miles an hour, 60 times 1,609, well, that will get us to if we just did that calculation, it would get us to meters per hour. So we're heading in the right direction. And then if we divide by 3,600, that will give us our answer in meters per second. And if I type that into the calculator, so if we look there on the calculator, this is how we type it in. Press this fraction button, and we get, what was it, 60 times 1,609, and then the down button to get it down there. 3,600 equals, gives it as a fraction, is the most accurate. So we can either press SD at this point, which will give us it in this form, and I'll show you another way in a sec, 1 second. So that was 26.82 meters per second. So when you're traveling at 60 miles an hour, you're actually going at 26.82 meters every single second. Now I did say you can either press SD, or there is another way, because it's a fraction and that sort of decimal would go on forever, so it's not a completely accurate answer. The way of actually doing this is if we typed in the same equation again, the same mathematical operation, times 1,609, and then over 3,600. And now rather than press it, if you look just above the equal sign on most of these Casio calculators, you'll see there's a wobbly equal sign, and that's a roughly equals to. So if you and anything yellow, you have to hit the shift first. So shift and the roughly equals gives you the decimal or the rough answer straight away. It's still more than accurate enough for what we need. Okay. So as we can see here on the document, this can be represented by a graph, and this graph, if we're to draw it in, so if we look at the graph and we have a graph of velocity, and imagine we've got a graph a line that goes straight up like this, then the area under this graph, because this here is velocity and this is time. Now velocity is measured in meters per second. Time is measured in seconds. So this will be the velocity that it gets up to here. Now the area under the graph is equal to the distance or the displacement, how far the object has travelled. And actually this should be obvious, shouldn't it? Because if we look at the two units here, we've got this area is going to be, in this case, it's the area of a triangle, isn't it? So S, displacement in this case, is a half, area of a triangle, half times base, which in this case is t, time, times velocity. Well, just looking at these two bits here, time is meters per second times seconds. Well, if we multiply them together, we get meter second over seconds. So the units, these would cancel out, seconds. So we're left with meters. So the result of this area must be displacement in meters. So if we want to calculate the area under this graph, it will give us displacement. Now this graph can also, it doesn't need to be something accelerating like this, go from zero velocity up to maybe 60, 70 miles an hour. It could be that this graph shows a constant. It could be that this graph shows a constant like this. So we've got velocity and time still. But now the area under this graph is all of this area here. And the way to obviously work this area out here is to do velocity times time. The only other graph we're likely to see, let me just highlight this and move it to the side a little bit. The only other graph we're likely to see, I'll just draw it freehand, is a graph that goes like this, decelerating, so going from a velocity down to zero velocity to stop or slowing down. We might see one that's a combination, like if we were travelling in a car down a straight road, we go from zero to a velocity, we stay at that velocity, and then we decelerate. Now the only way to calculate this is to work out the area of each section. The acceleration, the constant velocity, and the deceleration bit at the end. Work them all out, add them all together, and that will give us our distance. So with this one, the only way to calculate this is to do all three, add them together. So calculate the area of this first section, calculate the area of the middle section, calculate the area of the end, add them all together, and this will be distance travelled. Of course, the gradients to these lines, any of them, is the acceleration, whether that's negative, decelerating, or positive, accelerating, or zero, constant velocity, just going at a constant, when we're on an aeroplane, going at 500 miles an hour, constant zero acceleration. So that's from calculating the gradient. The one you won't see at this level, but you may see at a higher level, and this is common in the real world, is a curve. Now obviously this gets far more tricky to work out the area. The gradient will be different the whole way along. But when you come to do calculus, calculus is very useful for this. When you're doing differentiation or integration of the area under curve, differentiation, the gradient at any point. So you won't be touching on this yet, but when you do touch on calculus, this is a really good use for it. Okay. Then the other method, is to use one of these five calculations. One of these five equations up here. They're often referred to as the SUVAT equations. So if you can't remember them, type SUVAT equation into your phone, SUVAT, displacement, initial velocity, final velocity, acceleration, and time. And you'll get this picture that tells you all of them. So it's not as hard to remember as it used to be. Now I've got phones and you can just look at this on the internet anytime. These are the equations. Now what you may notice about these equations is that this first equation here has everything in it apart from S. I'm going to put S at the side because it's missing an S. It's got all the other terms in it from SUVAT apart from S. This has got S in it, it's got U in it, it's got T, it's got A, it's got T again, it's missing V. This equation, it's got S, U, V, T, it's missing A. This equation, it's got V, it's got U, it's got A and S, it's missing T. This final equation has got S, it's got V, it's got T, A and T, it's missing U. So each of these equations is missing one of the SUVAT terms. So when we're answering a question, what we're going to be looking for is which equation we need to use each time, and that's what the skill comes here, being able to know which equation is appropriate when. So we're going to have a look at the first question that we've got here, and we're going to look at it in both a graphical method and a... So we're going to look at the first question here. First of all, we're going to do the calculation graphically, then we're going to do the calculation algebraically, and hopefully they're going to come to the same answer, otherwise we've got a problem. That's another use for the graphical method algebraic, is that you can do it two different ways to make sure you get the same answer. and it's a bit of a check to make sure you've got the right answer. You will notice also in the question sheets that I always put in these square brackets at the bottom the answer. That doesn't mean you shouldn't have a go at them. What it does mean though is you can check your answer to make sure you're not doing them all wrong, and then you find you've done 20 questions and you've got the wrong answers for all of them, you just wasted all your time. Let's have a go at the first question. Do it graphically first, and then we'll have a go at algebraically. So, Q1. So, a particle is accelerating uniformly, and when we say uniformly, what we mean there is a straight line. We don't mean a curved line like this, we mean a straight one, okay? So every word in here has some meaning that we need to take from it. So a particle, that means that like an object, is accelerating, it's got a gradient. Uniformly, so it's an upward slope, uniformly, from rest, so that after 10 seconds, it has achieved 15 meters per second. Find its acceleration and the distance it has covered. So, well, let's do it graphically to start with and draw it out, so we know what's happening. Well, we've got no conversions to do here because it says it's going at, we've got velocity here, 15 meters per second. That's the velocity it gets to. It starts at 0 here, 0 meters per second. And it does this in time, and the time it says it does it in 10 seconds. So, first bit we've got to do is to work out the area under here. So S, in this case, the distance travelled or displacement, is going to be equal to this area. Well, we know that's equal to half base times height. So half times the base, which is 10, and the height is 15. And that's equal to 75 meters. That was easy enough to do in my head. And now the next one is to work out the gradient for the acceleration. So the gradient really is the change in y, change in the y-axis divided by the change in the x-axis. Now in this case, it starts and ends at 0 for both of those axes. So it does make life a little easier, but we will write the equation out in full. So acceleration is equal to the change in y. Well, it goes from 0 to 15, so the difference between 15 and 0, that is 15, but I'm going to write it there just to make sure I know what I'm actually doing. And the change in x, well, it goes from 0 to 10. And that's basically the same as saying 15 divided by 10, which is 1.5 meters per second squared. So that's our graphical method. The next one is the algebraic method. So when I'm looking at a question like this, I'm looking at words like rest, 10 seconds, meters per second. So I'm automatically trying to put these, and I put them in the form that they're in the equation. So I'll look at this and I'll say that t equals 10. Rest, well, it starts from rest, so that's its start velocity, so u equals 0. It gets up to 15 meters per second, v equals 15. Any other information we've got there? No, we just got those 3 bits of information. Okay, so now we need to find an equation that has all 3 of these in it and also has s, because we want to work out distance or displacement travelled. So we can't use this first equation because it hasn't got s in it. There's no point in using that one. So we need an equation that's got s in. Well, all the others have got s in. We don't have acceleration at this point, so that kind of rules out this one, and this one. So the only one it leaves is this one, because this has got s, but hasn't got a, and we haven't been given a at this point, acceleration. So we can only use this equation here. So for acceleration, sorry. So in this case then, our displacement algebraically, s, we use the third equation there because it's got s and it doesn't use acceleration, is u plus v over 2 brackets around it times t. This really is just the area of a triangle, isn't it, though? Anyway, I'll type that into the calculator. So let's see how we type that in. Use the fraction button. Draw it as it's supposed to be there. Use the brackets. Well, it starts at 0 and v gets up to 15. Close brackets. Move down. Divided by 2. And then use the arrow to move to the side. Times. Time is 10. 75. Gives us the same answer as we had before. And if we do the acceleration one as well, which equation we're going to need for acceleration? Well, none of them start with a, so we're going to need to rearrange an equation, whichever it is. It's got to have a in it, acceleration, so that rules out number 3. Now we've calculated s, and it was a round number. It's quite accurate, but quite often s will come out as a fraction or as a really long decimal, and you have to round it. So I would advise against reusing a number you've just done a calculation on. So really, we're looking for something that's got a in it, which rules this equation out, and we're also looking for something that hasn't got s in it because we weren't given s; we've just calculated it. So the only equation here is the first one because it's got s. Sorry, it hasn't got s. It has a, and it's got all the other terms we need. So let's look at this equation. It says that v equals u plus a t. Well, if we rearrange this equation, let's do it step by step. First of all, if we use our BIDMAS, we'll get rid of, we'll move the u over to the side, so we get v minus u equals at. Final step is to get t over the other side, and if we divide both sides by t, that will move that, so we get v minus u over t equals a, our acceleration. In this case, our v is our final velocity, 15, minus 0 over time equals 1.5 meters per second squared. So that was fairly straightforward how to work that out. Most of the problems you're ever going to have if you're at uni or you're doing a HNC or BTEC or an access course, when it comes to the question, is interpreting the question and understanding what it's actually asking for. So that's why if your English skills aren't particularly great, some of these terms might not, like the example rest. We're not talking about sitting down, having a sleep. We're talking about being still. But that might not be obvious for some people when English is a second language. So let's have a go at the next question. Question 2. So a car accelerates uniformly, straight line. I'm going to just have a go at this one, start with algebraically, then we'll have a go, we might have a go graphically. A A car accelerates uniformly from rest. So as soon as I'm reading this question, uniformly from rest, u equals 0. That's what I say immediately. And after 12 seconds, t equals 12. Has covered 40 meters. That's a displacement. S equals 40. What is the acceleration and its final? What are its acceleration and its final velocity? So we've got three terms here: u, t, and s, and we're being asked to calculate acceleration a and final velocity v. So let's have a go at that. So we're going to need an equation. First of all, we're working out acceleration. It's got to have a in it, so that rules out equation 3 immediately. And we're looking for something that's got u, t, and s in it. U, t, a, and s. That's possible. We can't have v in it because we don't know what v is. So that rules out. So it's going to have to be this one because it hasn't got v in it and it has got s, u, t, and a. So we're looking for a. Well, we can do a little bit of a cheat on this one. Let me just draw a line there to separate these. We can do a little bit of a cheat on this one. We're going to use this equation that says S equals ut plus half at squared. So this basically, if we looked at the graph, it's accelerating uniformly. We don't know what v is. We do know that this is 12 seconds, and we know the area here is 40. So something times a half times v will give us 40. So if we look at this equation here, we need to rearrange it for a. Now, rearranging equations is fairly straightforward, but we can make life a bit easier for ourselves here because we know that u in this case is 0. So we know that anything times 0 is 0, so that does not need to be rearranged. It's going to cancel out anyway. It doesn't need to be moved. So we're left with s equals half at squared. This is another way of calculating the area of a triangle. Half times the gradient times the base squared. So if we rearrange this now, it's a bit easier without that ut there. We get we're going to rearrange this for a, and we get s equals, when we rearrange it, we're going to get a equals s over half t squared. So s is 40 over half times t, which was 12 squared. So if we type that into the calculator, let's see how we type that in, because we've got a bit trickier to type in now. So we use the fraction button again, 40, and then move down. This time it's a bit more difficult. I'm not going to use the fraction of a half because I know that half is 0.5 times 12 squared. So if we put 12 and then squared, that should give us 509, which if we press the SD button is 0.55 or 0.56. Let's say round it up, 0.56 meters per second. So The next bit it asks us to calculate is what's the final velocity. Well, this is a time as well where I said about before, where we need to be careful when we use those equations up there. I've rounded this value here for acceleration. If I were to use that again, I would compound that error. So I'm going to say I don't want to use acceleration in my next calculation to work out velocity. So I'm looking for an equation that hasn't got a in it. So this is the only one left here in the middle. So it's S equals U, which we've got, V, which we want, T, which we've got, 2. So we need to rearrange that for V, sorry. S equals U plus V over times T. So first bit with our bid mass when we're rearranging is to move that T over the other side. So S over T equals, well, U plus V over 2 would be the same as writing half times U plus V. Well, that would be the same as, if we multiply it by 2, we get that over the other side. So we can say that 2S, careful, my S's and 5's look very similar, divided by T equals U plus V. We take U away from both sides, we're going to get V equals 2S over T minus U. Now in this case the U is not going to do a great deal for us. So if we plug those numbers into that, we get 2 times S, which is 40, over T, which is 12, minus U, which is nothing, it starts from 0. So then, if we type that into our calculator, clear it first of all, and then we go 2 times 40 over 12 equals 6 meters per second, and that's both answers to 2. Now we could do that, we could draw it and calculate the gradient and calculate the height here from our trigonometry, but I'm sure you're all okay with having a go at that. So let's work that out with the graph. Well, if we imagine what this graph's going to look like, just move down a bit more. Nice and big. Always draw it fairly reasonably sized. I'll show you how to do this in Excel as well in another lesson, which will is a lot neater and easier to do. But for a diagram, just try to get that down a bit. Wrong place. So there's our graph. Now we know that the area under here is 40. We know that it starts at 0, and we know that this is 12. So before we can work out the gradient, we really need to work out the velocity. So we can do that because we know that we'd normally work out the area of a triangle. I'll put that as S because in this case area is our distance travelled. So S, we'd normally work it out, is equal to half base times height, which in this case is so half of our base, which is time, times our height, which is V. But we know time, we know S, so we just need to rearrange this equation, and it basically gives us, well, we'll have a look. So it gives us 2S, and then divided by V, which equals and divided by T, which gives us V. Well, in this case, that's going to be 2 times 40 over 12, which is the same answer as before, or 6, so we did get that right. And I think we said before from that equation when I was talking up here that the gradient and triangle area can be calculated. So the area, or S, is equal also to half A, the acceleration, or this gradient, times T squared. If we think about it, if we made this here into a box, a square, and then multiplied by the gradient and then half, it will give us the half of that sort of square, won't it? So if we rearrange that for A, because again, we don't want to be using this rounded figure in our next calculation, so A will equal 2S over T squared. I'll type that in. 2 times 40 over 12 squared, 0.55 like before, 0.556, different round accuracy. Okay, so that's two ways of calculating, that's two ways of calculating the same thing. So let's have a look at question 3. So with question 3, a train uniformly retarded, that means slowing down, that's the correct usage of the term, from 35 meters per second to 21 meters per second over a distance of 350 meters. Calculate the retardation, the rate at which it's decelerating, and the time taken to come to rest from 35 meters per second. Now this is a tricky question and it's in the wording. So let's have a look at this. So first of all, we're going to draw a nice big graph. Well, it says that it starts here at 35 meters per second. And if I was thinking about this in terms of algebra, I'd be saying that u equals 35 because it's our start velocity. It then says after a period of time, it doesn't tell us how long, but it says a period of time, the train is travelling at 21 meters per second, so we'll put here. Now, what we do know is that in travelling this distance here, the distance it covered during this time was 350 meters during this area here. So V in our algebra, V is equal to 21. Actually lower this time, the final velocity, because it's slowing down. And we know that S equals 350. Calculate, first of all, the retardation, the slowing down. So, how would we do this? Well, we'd have to look at gradient here if we're doing it graphically. And graphically, the acceleration is going to be equal to the change in y divided by the change in x. And we don't know what that is, so we'd have to calculate that. So in examples like this, you're far better off using the algebraic terms, but I would always draw this in your assignments. I would always sketch this out, just so you've got a clear idea in your head exactly what's going on. So the first bit is to work out the acceleration or deceleration, in this case, which is negative acceleration. Well, if we look back at we've got U, V and S and we're looking for A. Well, if we look at this, so we've got U, V, S and we're looking for A. So U, so we can't use this one because it's not got U in it. We can't use that one because it's not got V in it. So it's down to these two. They've both got U, V, but we haven't got time. So it's going to have to be this one because this has got V, U, A and S. And we're looking for A and it's got everything else that we need. So we'll go with that equation there. So that is V squared equals U squared plus 2AS. Now in this case we are looking to try and calculate A. So if we rearrange that equation, we're going to get A equals, just move everything around, we'll get V squared minus U squared over 2S. So there's an important point to note here coming up about using your calculator with negative numbers and squaring them. Okay, so it's a key point. So here, A is going to be equal to V squared. Now V was 21. 21 squared, take away 35 squared. This is going to give us a negative number. And, divided by 2 times 350. So get the calculator back up and so I'm going to type this calculation in. Use the fraction button. So 21 squared minus 35 squared over 2 times 350. I should just put 7 there. And that equals a negative 1 point. It's the negative, I'll have to say it. Minus 1.12 meters per second squared. Now, that is the right answer. Yep. Bear in mind, this is an accurate thing to write on your assignment. That acceleration is equal to minus 1 1.212. It wouldn't be accurate to write in your assignment that the deceleration was minus 1.12 because deceleration is already negative. And if you leave the negative in front of it, you have a double negative. So a negative deceleration would be an acceleration. So if you're writing about deceleration and you put A at the beginning, then you need to put a negative. If you're writing about a deceleration, you don't need the negative there because the deceleration is already telling us that it's negative, that it's slowing down. Okay, so that's its rate of deceleration. The next bit of the question, this is the bit that's really tricky. It's saying, how long does it take it to hit here? How long does it take it to stop? Well, we can calculate this because we know it's deceleration and we know this gradient should stay the same throughout the rest of the question, throughout the rest of its travel when it's coming to rest. So, we're going to need to use acceleration this time. We're going to have to. And we're going to work out how long it's going to take. Does it say how long it's going to take? Time taken to come to rest. So let's have a look. How long will it take to come to rest? Well, we know u in this case, we're going to have to change these numbers a bit. We know that u is going to be equal to 35 still, because it starts at that velocity. But now v, we're working out when it comes to rest, 0. And we know a, our acceleration, is minus 1.12. So that should be enough information. If we look at the first equation there, we get v equals u plus at. If we rearrange that for t, we get t equals v minus u over a. Remember to use the negative there. So t equals 0, take away 35 over minus 1.12. Now, get a calculator out. This is where the negatives are going to be important. So the first bit of the calculation is 0 take away 35, which is going to generate a negative 35. And then take away, move down, negative. Now don't use the takeaway sign, use the negative sign here, look, just above store. Negative 1.12. And because they're two negatives, they cancel out and give us a positive. We obviously can't have a negative time value. That's definitely against the laws of physics in this case. So that comes to 31.25 seconds, which is what it does.